Hello, this is Colton. I'm here to make up Lab 11. We're doing properties of liquid crystal cells, and as you can see I'm here by myself, and I'm going to be the filmographer, cinematographer, and lab lackey today. So first I'd like to show you my setup. So what we've got here first is our helium neon laser, and it's passing through a set of polarizers. This is a 90-degree polarizer, and this is the 0-degree polarizer. So what we have is effectively cross polarizers right now in this current setup. In the center we have a Friedrichs liquid crystal cell with the many wires coming off it to various things, which I'll explain later, and a detector to measure the transmission change as we apply a voltage across the liquid crystal cell. We also have our function generator, and we're generating at about 2 kilohertz right now, square wave, peak to peak 1 volt. We have our defective oscilloscope, which is reporting voltages of 128 volts. And to bypass the silly oscilloscope, we have a multimeter to show the actual voltage across the leads. So what I'm going to do is actually show you graphically, or show you on the multimeters first what's going on. And as you can see, I've got a voltage of approximately 6.186 volts here applied. But as I change the voltage, we're going to watch the signal to the detector modulate as I decrease and increase the voltage. And as you can see here, it's going up and going down like a sinusoid, like we expect. So, pulling up our handy-dandy plot on the computer. Looks like it's not loading like I thought it was going to load. We can see the sinusoid that's created when we plot this out. And it looks like we've had a little bit of undersampling here. As you can see, it's not a perfect sinusoid, but you can see that what happens is that when you get a quarter wave of retardance, let me start over. So the valleys here represent a half wave of retardance, while the peaks represent a full wave of retardance that the LCC is producing. If this were perfect, they would all probably be at the same level. And as you can see, as we go up, it just stops. The sinusoid stops and goes to a straight line. And what I'm hypothesizing is that the LCC is actually acting now as a quarter wave linear retarder because it's saturated out. So that's basically what we did. And the next thing after we figured out what that was is that for each of the cells we then rotated the polarizers so that instead of having extinction allowed for max transmission, and what we saw is that we had a flip in the sinusoid, so it actually started at 0 and then peak to peak at a different location. We didn't do the polarimetry stuff in this lab because everything was broke and we couldn't get it to work. So gave it my best shot this week. This is Colton, Lab 11 signing out. Thanks.